Hello, hello. Welcome to our session. Probably this is the first session today that you'll be hearing about AI infrastructure and TPUs and agents, so play along with us here. My name is Gurmeet Goindi. I go by Gigi. I lead some of the product management aspects of TPUs. I have my colleague Cheng here who will go share his details on some GPUs, and we are very lucky to have two of our customers, Minho and Giovanni, who will talk about their experience with our AI infrastructure. We will keep some time at the end of the question for Q&A, and if we run out of time, we will be here, so please come back and have a discussion, and we'll be more than happy to go deep or broad, whatever works best for you. The focus of our session is want to share the philosophy that Google has while building its AI infrastructure. It's deep-rooted in Google's multi-decade experience in running large-scale distributed systems, and we will discuss how we bring this to you in a very easy consumption manner, either if you're using our own silicon TPUs or our partner silicon GPUs. We'll go as deep as possible in this session on those two. Numbers speak a lot for themselves. So we have been the leading AI infrastructure provider in the industry, and one of the biggest customers we serve is us. So today, if you see, almost 9 out of 10 AI labs use our technology, including us. At the same time, over 2 billion people experience on a daily basis of what AI can do for them using all the Google properties that you are very familiar with. When we talk about the amount of throughput this system, our infrastructure delivers, we do over 10 billion tokens per minute. I've been speaking for 2.5 minutes. By this time, we have processed 25 billion tokens in a very reliable, resilient manner. Last but not the least, when we run these large-scale systems, we take a lot of learnings on how to optimize these systems, how to make it efficient when it comes to availability, when it comes to resilience, when it comes to power, and we bring it back for you to consume via GCP. In the last few years, even Alphabet has been able to reduce 78% of their serving cost using this infrastructure. And this is relevant to you as well. Diving us a little further, what approach that we take while we are thinking about this infrastructure? First and foremost, our AI hypercomputer, which we'll dive a little bit deep in, is co-designed right from the chip to the frameworks that consumes it. We take our distributed system approach and ensure that each and every component of the stack is co-optimized for you. So you're not just consuming silicon, or you're consuming a fully battle-hardened system. And where we have taken the extreme efficiency to a different level is how power efficient these systems are. And it's a win-win for being a very green, resilient system at the same time lowering down your TCO. Last but not the least, these systems are not, like my last slide said, they're not giving you an experimental workload, or I'm trying one thing and seeing how it works. These are large-scale deployments, completely hardened. You can start really small and go up to thousands of chips in a matter of a few clicks, and the system will perform as if it performs for the entire Alphabet. Who has heard about agentic workloads? I think that I'm talking about this for the first time. What's the core of an agentic workload? The core of the agentic workload is the compute infrastructure that makes all of this happen. And that's what we call the AI hypercomputer. It's an idea that we have fulfilled by bringing a lot of core technologies together, in which right from the storage layer to the network that binds these compute elements to the compute elements itself, to the software stack that helps you consume these compute elements, have been rethought, rebuilt, put together to serve AI workloads. Moving us a little further, sorry, I collected one too many. There you go. So what constitutes the AI hypercomputer? Isn't just a collection of product. It's like a unified, co-designed architecture across this Google's and NVIDIA's hardware, specifically tuned for your agent-first world. Here, the foundation layer is our purpose-built TPUs or our partners' GPUs. At the same time, what brings it together is our open software layer. Here, the developers have full flexibility to use JAX, PyTorch, XLA, utilize inference agents like VLLM for their training, inference, or serving workloads. The cloud also enables them to give a very flexible way of consuming this. So you can use on a spot pricing basis to have all the way to have long-term commitments with us, which we call CUDs. So we enable not only just the technical aspects of the system, we also give you commercial fungibility to consume this. Let's go a little bit deeper and see what our typical pre-trained. How many of you use GPUs or TPUs for training today? How many of you are using them the same for inferencing? Brilliant. So we'll go on both sides, what we do for training and what we do for inferencing. So if you look at pre-training is the ultimate stress test of the infrastructure. It's complex, and it's a balance where even a single bottleneck between your storage, compute, and network can bring your multi-million-dollar model to a halt or make it less efficient. Hence, we invest a lot in making sure this stack flows very well, right from the storage, whether it's managed Lustre or our KV cache called the Anywhere cache, or it's the core of the product, our TPUs and GPUs, or it's the frameworks that bring this together. That's JAX, PyTorch, our own MaxText. Pardon me. But what brings it together for you is the orchestration that we bring it with GKE and Cluster Direct. So when you think about pre-training, all you have to worry about your models and how the infrastructure that you need for your models. We make sure the storage works for you. We make sure you are able to orchestrate it. We make sure you are able to load balance it. We make sure that the system remains up for maintains the resilience and the availability that you desire for your training workload. Now, if you take a step further in the inferencing side, it's a similar story. The inference request goes to the JKE inference gateway, which routes based on the request parameters and the load on the system to find the best target for it. Models are deployed to GKE clusters. We provide first-class support for VLLM and seamless compatibility across GPUs and TPUs. Customers can use dynamic workload schedulers to get capacity where they need it. At the same time, we leverage an AI-optimized cloud storage system to store model weights, cache the data, and give you the resilience and the availability that you're looking for. Let's go a little bit further. When we talk about agentic AI, it's not a one-time linear process. It's a continuous high-speed loop of data processing, training, inference, and reinforcement learning. And we don't use one-size-fits-all approach. Instead, we provide specialized stack for each of these phases of the workload that we are trying to do. On the left, you see the heavy lifting stack of data processing. This utilizes high throughput hardware like the newly announced TPU 8T and the AX5 compute. And on the right side, we pivot the inference and the reinforcement learning like stack, which you can use the TPU 8i instances or G4 instances. And my friend will talk a little bit more about G4 instances as we go forward. To manage all of that, we provide tools like GKE Agent Sandbox and Inference Gateway, supporting frameworks like VLLM and Ray to simplify how you deploy this infrastructure at scale. We have two proven accelerator platforms, the Google Cloud GPU platform with NVIDIA and Google Cloud TPU platform. On the GPU side, we offer the complete portfolio from the G2 L4 for low-cost inferencing to the A4 Max GB300 systems, which are designed for exascale performance and features of Google Advanced Liquid Cooling. On the TPU, we had the purpose-built accelerators from TPU v5e all the way up to the latest 8th generation TPUs, which are coming soon at the end of the year. The key takeaway here is we provide the right tool for every AI workload, from mainstream inferencing to frontier models. I'm running a little bit short on time, so I'm going to skip some slides. But everything I talked about, the AI hypercomputer, the agentic stack, what we do for inference, what we do for training, at the core relies on the silicon. And Google took this bet that the specialized silicon will be the key vehicle to deliver enterprise-grade AI experiences almost 10 years ago. We started this journey with TPU v1 in 2015, and you saw the announcement today. We had the latest innovation with the TPU 8T and TPU 8 High that will be available, that was just announced today. Let's go a little bit more deep on how we have used TPUs in a system. Now you will say, great, you had chips for 10 years, but do they work? As you see, the TPUs are just not the new tech. They are the silent, battle-tested engine that has powered Internet's largest platforms for over a decade. If you look on the icons on these represent 9 different Alphabet properties and services, which include Search, YouTube, Gmail, Maps, and each of them serve 1 billion users. And every time when someone searches for information or watches a video, they are likely interacting with our TPU infrastructure. And when you subscribe to the AI hypercomputer, you get a slice of that infrastructure for you that has been battle tested by Google for so many years. Let's go slightly more deep at how we are able to provide this kind of a scale up and scale out with GPUs. Now, if you look at the sheer physical muscle that comes from the AI, for the AI supercomputer is how do we scale up right and how do we scale out right. On the left, you see the Ironwood TPU v7. This is a scale-up powerhouse. It's in a single chip-to-chip domain. You can have up to 9216 TPUs clustered together, close to 2 petabytes of DRAM, 1.77 to be precise. And everything within this pod is connected with 9.6 terabits per second, allowing you researchers to treat these thousands of these chips into a singular supercomputer. With the TPU 8T that was announced today, we further pushed this from 9216 to 9600 chips in one cluster available to you to consume as a single entity. And we also doubling the bandwidth within the system with the 8T generation. I'm going to skip this in the interest of time, and we will talk a little bit about what you're really come to hear about, is our latest and the greatest TPU systems, TPU 8T and TPU 8i. This is the first time Google is releasing 2 different platforms fine-tuned to specifically tuned to 2 different type of workloads. TPU 8T is our powerhouse. This is optimized for training high throughput workloads. You can put together close to 9600 chips in one. And TPU 8 High is a breakthrough platform that's optimized for ultra-low latency inference and reinforcement learning. Let's go a little bit more in the details, and this will give you an idea when I say how big of a powerhouse it is. When it comes to training a trillion parameter model, you need a system that can scale. TPU 8T scales far beyond what we have ever built. You get 121 exaflops in one superpod. It's 2.8x the performance of the prior generation, which we released a year ago. So that tells you the scale of innovation Google is bringing into our silicon. At the same time, TPU 8T clusters have up to 2 petabytes of high bandwidth memory. When you talk about TPU 8i, we push the innovation to support your low latency, high throughput inferencing workload. This one is optimized for inferencing and reinforcement learning. We triple the SRAM from a previous generation's TPUs to 384 megabytes, and at the same time, we increase the HBM bandwidth, what you call the high bandwidth memory, by 50% to 288 gigabytes. This chip enables you to keep more of the agent's working memory, the KV cache, right on the chip, not on a separate cluster or the system. The modern picture of expert models required accelerators to talk continuously and synchronously to each other, and TPU-8i is a solution for doing that. But don't listen to me. I will invite Minho from Kakao to tell his experience on using TPUs on Google Cloud. All yours. I will take.
Right. Thank you, Juji. That was a great overview of what the TPU platform can do. Now, I'd like to show you what it looks like when the platform meets a real production workload. Hello, everyone. My name is Minho, and I'm an ML research engineer from Kakao. I work on both pre-training and post-training of our LLM foundation models. For the next few minutes, I'd like to share how we've been building large language models on Google Cloud's AI hypercomputer and what we actually observed along the way. Kakao is part of daily life for almost everyone in Korea. Kakao Talk is the messaging app that nearly the entire country uses every single day, and Kakao is also present in mobility, payments, banking, and many other services that people rely on. What ties all of this together is our mission. We want to build a better world through technology and people with a focus on user-centric design, bold innovation, and honest communication. And today, the frontier of that mission is AI. This is Kanana, Kakao's in-house AI brand. The name combines Kakao, native, and natural, and it reflects what we want Kanana to be, an AI that feels native to our services and natural to the people using them. Kanana is a layer that makes those everyday Kakao moments smarter and more personal. And because it sits so close to our users' daily lives, getting it right means that infrastructure underneath has to be rock solid. That's where our story with Google Cloud TPU begins. Kakao's journey with Google Cloud TPU actually goes back quite a long way. Back in 2020, we had built CodeGPT, one of the earliest Korean large language models on TPU v3 and v4. That was where we first learned how to operate TPUs at scale. Then, as we moved up to our Kanana series, we scaled onto TPU v5e and Trillium. Each generation gave us meaningfully more compute and better efficiency, which is exactly what we needed as our models grew larger and our training data grew longer. The point I want to highlight is that this has been a real co-evolution. Every new TPU generation unlocked a new class of model we could learn, we could train, and every ambitious model we planned pushed us to adopt the next generation of hardware. But great hardware alone isn't enough. To actually extract performance from these TPUs, the software stack matters just as much. When we trained our Kanana models, we used MaxText as our training pipeline, and what you're looking at on this slide is essentially the entire training stack we rely on. Starting from the left, you can see the full training pipeline from data format and processing to modeling, optimization, and checkpointing. Underneath all the sits, jacks, and XLA, and at the bottom, the TPU itself. Every single block in the diagram is built by Google, top to bottom. That is not just a branding observation. Because these components are co-designed, they work seamlessly. The APIs fit together, performance optimizations propagate naturally from the compiler down to the hardware. And the developer experience stays simple. For us, this meant we could focus on modeling these decisions instead of fighting with infrastructures. Now, raw throughput is only half the story. What really matters is goodput, the fraction of your word clock time that's actually producing useful training progress. Nodes fail, jobs crash, checkpoints need to reload, and every hour spent not training is compute you've paid for but haven't used. This is where the other half of AI hypercomputer comes in, TPUs on GKE. On the JAX AI stack side, MaxText and XPK let us scale up and out effortlessly, spinning up hundreds or thousands of TPU chips with just a few commands. On the GKE side, we get automatic recovery from node failures and dynamic rescheduling, so when something goes wrong at scale, the job resumes from the latest checkpoint on its own. Put the two halves together, and you get not just high throughput, but high goodput. Let me close with some concrete numbers from one of our Kanana small training runs. We trained on 10 trillion tokens using 3 full TPU V5E slices, which is 768 chips in total over roughly 30 days of continuous training. Here's what we observed. We sustained 45% MFU throughput throughout the run. And for anyone who has trained large models at this scale, that's a really strong result. We also achieved 99% throughput with 0 node failures over the entire 30 days, not a single one. When I look at these curves, what strikes me most is what's not there. No sudden drops, no gaps, no restarts. Just a full month of clean training, which meant the infrastructure disappeared into background and let us focus on the model itself. So to wrap up, at Kakao, we've been on this journey with Google Cloud TPU for more than 5 years now, from CodeGPT all the way to the Kanana. Throughout the journey, the combination of purpose-built TPU hardware, the coherent JAX AI stack, and GK-based orchestration has let us focus on what we actually care about, which is building better models for our users. Thank you so much for listening, and I'll hand it to Cheng.
Thanks, Minho. All right, well, 99% goodput with 30-day non-destructive training run. That's very impressive. That's very impressive. Let's switch gear a little bit. Let's talk about GPUs. So Google, in fact, Alphabet overall, has a long-standing partnership with the NVIDIA since the early days of AI, right? So we at Google Cloud, our GPU strategy has really been two things. One is first, one is best. What do we mean by first is we strive to be the first hyperscaler to market with NVIDIA's latest GPU platform. What I mean by best is that we want to provide the best cloud services, best implementation of a cloud services that sort of goes around, built around them. As you can see from this chart here, from Hopper generation to Blackwell all the way to Rubin, we really offer a complete product portfolio for all the AI applications and across all your ML lifecycle stages. Today, I'm going to focus on two new products. One is our A5X, which is our product offering based on NVIDIA's Vera Rubin product. And I'll also be touching on our G4 product, which was launched earlier this year. That's based on NVIDIA's RTX Pro 6000 product. We're really excited to announce that in the second half of 2026, we will be offering, among the first to offer NVIDIA's Vera Rubin's NVL72 systems in Google Cloud. The product name is going to be A5X for us. A5X will be powered by the same Google AI hypercomputer infrastructure that Gigi was just talked about. It basically comes with the support of, first, resilient AI orchestration layers that has the self-healing infrastructure, this predictive analysis capabilities that build in. Also comes with integrated first-class services like our entire unified AI stacks, from GCE to GKE to Cloud Run to Vertex AI, all building and ready to go with Vera Rubin. And it also comes with all the flexible consumption model that Gigi also mentioned, reservations on demand as well as DWS with both Flex and calendar mode. So please be on the lookout for our preview announcement later this year. Now let's talk about the G4. The reason I really want to bring G4 out in this session is, personally, to me, I feel like G4 is the Swiss knife type of GPU product that's really versatile for all the agentic workloads. These days, I think agentic AI is really top of mind for many, many customers, and I think G4 can play a key role in all of that. The reason I'm saying that is three things. Number one, it has a really versatile and robust compute platform. What I mean by that is essentially RTX Pro 6000 Blackwell as a GPU is one of probably the most versatile GPU on the market today. Secondly is we also offer very generous memory, local storage, and networking throughputs for the platform, so that the product itself is very, very scalable in terms of different use cases. Lastly but not leastly, we also offer a wide range of different sizes of virtual machines where you can actually run anything from the smallest inferencing model experiences all the way to even a large language model, reasoning model training work. The other thing is that if you want to run a larger model, if you want to work with a larger model, we also invested this P2P, peer-to-peer network acceleration capability, really aimed to significantly improve the GPU to GPU communications. On the 4 GPU VMs, we observed about 2 times NACO communication performance improvement. On the vGPU VMs, the performance gain can go up to 2.2x. What it really means for you to run the workload really is that you can expect to see, by leveraging P2P, you can expect to see token throughput to go up roughly by 2.7 times. And then your token latency, meaning inter-token latency, can reduce by approximately 41%. So that's pretty significant. And it's super easy to use as well. To turn it on, all you need to do is just turn on an environment variable. So really looking forward to some more feedback on that. In addition, we also partner with NVIDIA to enable vGPU on G4 VMs. And what it means is that this allows us to offer fractional GPU shapes in our virtual machine offerings. And this would allow you to standardize various AI applications, workloads on the single GPU type. Then you can right-size your compute instances to best match your use cases. Because we select also a fairly much powerful CPU on G4 than our prior generation. So I think what you're likely to see is the performance improvement can probably be out of the box for even the fractional GPU VM shapes. By the way, if you happen to have graphics or visualization workloads, the upgraded NVENC, essentially the encoder cores inside of the RTX Pro 6000 GPUs, will have significant performance boost for workloads that does encoding and decoding operations. So we actually, since launched the G4 to the market, we've seen rapid adoptions for G4 through a wide range of different industry verticals, from manufacturing simulations to large language model inference, to supply chain automation, to robotic automations. We can't wait to hear from what you will do with our G4 products and how you're accelerating your agentic AI journey. With that, I'm going to welcome Giovanni, the Chief Product and Technology Officer from AppLovin, to talk about their experience with Google Cloud's GPU products. Gio.
Great. Thank you. Hey, everyone. My name is Giovanni Ge. I'm the Chief Product and Engineering Officer of AppLovin. So before we start today, let me just do a quick check. So audiences, how many of you have heard about AppLovin? Please raise your hand. OK. So decent amount. I see a lot of people know AppLovin here because they work for AppLovin. Still, there's still a few people who know AppLovin. I appreciate that. So AppLovin is a mobile technology company that helps the business of all shapes grow. So no matter if you are, you own a business of an app or you own e-commerce business, you can potentially become AppLovin's client. So in AppLovin, we use AI and ML to help the advertisers to connect to their best users at the best time with the best scale. So despite our low public awareness and presence, AppLovin actually touches the lives of many of us. So if you take out your cell phone and if you see that you ever played the mobile game in iOS or Android devices, there's very, very high chance that game that you play has a deep partnership with AppLovin. Sorry, I forgot. This is my page. I often describe AppLovin as a $100 billion startup. We are actually a public company with over $100 billion in market cap. But however, we operate like a true startup. Let me share a few numbers to illustrate that. So in 2025, we generated $5.5 billion in revenue. We serve over 1 billion daily active users in the global, in the whole world. Our ML-based ad bidding system handles over 100 billion ads requests every single day. And yet, to operate a product at this scale, all it takes is an extremely lean core engineering team with less than 100 people. So you must be asking, how is that possible? So well, to build a business at this scale with such a lean team, we have to be laser focused. We have to understand what to build and what not to build. We build only what wins us the market and never reinventing the wheel and relying on the right partnership to leverage a world-class infrastructure. And Google Cloud is one of those partners. By partnering with Google Cloud, we got 4 key benefits. First, demand elasticity. Our systems scale up and down efficiently and reliably with the Google Cloud. Second, CapEx efficiency. We don't have to manage our own hardware inventory and their life cycles. And then ecosystem support. By using Google Cloud, we get instant access to world-class managed services and toolings. Last but not least, the greater partnership. We continuously learn best practices by working closely with Google. One of the most important systems we run on Google Cloud at massive scale is Kubernetes. So most of the people here must be already very familiar with that. Kubernetes is a powerful container orchestration system that allows us to apply it flexibly across many different workloads. At AppLovin, our hyperscaled ad serving systems runs on Kubernetes. Our model training and model inferencing systems are built on top of Kubernetes. We also use Kubernetes for big data, research sandboxes, and AI workflows. It is so powerful and so versatile that it has become the foundational building block of our entire infrastructure. Here, let me share a concrete example. A year ago, our model inferencing system was built based on a simple architecture. We co-hosted multiple models on the same GPU. That architecture is easy to auto-scale, but it caused real problems. Over time, we found that our GPU utilization was low, and quarter-over-quarter GPU consumption went up dramatically. To solve this problem and stop this trend, we decided to tear the system down and build it from scratch. In this new design, we adopt a single modern tenancy architecture, which enables us to optimize the caching, batching, and the context management. In addition, We use Python to orchestrate workflows for fast iteration. For the meanwhile, we bind the native C++ processes to bypass the global interpreter lock, the GIL. We also build a model management system to handle model handle model control and versioning. This new architecture is very efficient, but to make it work, it demands a powerful and reliable auto-scaling mechanism and sophisticated network routing. Fortunately, Kubernetes gives us all of that, and we're able to solve the problem efficiently with Kubernetes. The results are significant. Last year, when we deployed this new inference server, we saw that our GPU utilization jumped from 45% to 75%. Our end-to-end overall GPU consumption was reduced almost by half. And more importantly, our inference latency also dropped significantly. Later that year, we reinvested this latency budget into scaling up our models, which drove significant and meaningful improvement in the business outcome. That's all I want to share. To summarize, we operate a massive scale product with an extremely lean team. And we're able to achieve this thanks to the great partnership with Google. Thank you very much. Thanks for listening.
It's great. I'm not sure I love the 50% reduction in consumption part, but I love the 30% utilization improvement. Don't you all like that? Right? 35% to 75%, actually 45% to 75%, that's awesome. Also, I love the latency reduction by 30%. That's great. That's awesome. Okay, let's wrap up, shall we? Okay, so again, I think the success story from Kakao, success story from AppLovin, very inspiring. Love to see all those success. Love to see like you all can take that away, implement that in your world. So what have you seen today? What have we talked about today? We talked about Google Cloud's approach for AI infrastructure, which is AI hypercomputer. We heard Gigi dive deep into our TPU infrastructure. You heard from Minho from Kakao to talk about how Kakao was able to leverage AI TPU, AI infrastructure to achieve 99% of the throughput with 3 months on training workloads. And then we talked about our offering for GPU on Google Cloud. You also heard from Gio on AppLovin how they're improving their utilizations for their inferencing workloads. If there's one slide to take away from the session, this will be it, right? This really is the 3-layer AI hypercomputer infrastructure that we built together that's being battle tested for all Alphabet workloads and has also proven to be beneficial to some of our customers already today. It builds from the foundation purpose-built hardware layer on the bottom, open software framework layer in the middle, and then very flexible consumption model to maximize your value on the very top. So we hope that you learned a thing or two about Google Cloud's unique approach to AI infrastructure, which is, thank you very much, AI hypercomputer, right? That's really our answer. The unique approach to Google, how we look at AI infrastructure is really AI hypercomputer architecture. And we hope some of you will be able to take those learnings and implement in your own environment. With that, I think we're going to ask you to provide feedback and open up floor for questioning. I think we have a little bit of time for Q&A. If you have any questions, why don't you folks come on up to the stage, and then we'll have the mic passed around and to answer questions. Thanks for coming, by the way. Thanks for staying till the end and staying with us, and thanks for being engaged listeners. I appreciate that.
You want to go down?
Any questions?
A little bit.
Oh, of course.
Hi, great talks. So this is me from Shopify. I'm leading the ML infra in Shopify, so we're doing initiative for AI as well. And I'm top 5 customers. So Shopify's top 5 customers were GKE as well. So I have 2 questions, maybe for AppLovin. You mentioned you're using on-demanding capacity. From our experience, that's quite expensive. So why don't you use reserve capacity if that's not a problem? Because if you have a large footprint, reserve capacity should be the go-to solution. But you're mentioning you're using on-demanding capacity. That's the first question. Second one is the inference improvement is really impressive. But I have a question about, is it mainly from the runtime and model itself, the optimization from runtime and the model itself, like the smaller and faster, and also from PyTorch to C++, but other CUDA kernel optimizations? Is there anything from GKE, like the gateway, the auto-scaling, all the things from Kubernetes? Is there anything from there? Yeah, thank you.
Does this work?
Yeah.
Okay, thank you for the question. The first question is about why do we run on a demand, not a reserved? Of course, we run on reserved to save the cost, right? But the accounting itself is a little bit more sophisticated than simple. On demand is cheaper, and on demand is more expensive, and reserve is cheaper. Because if you actually do the math a little bit more carefully, you will see that on demand usually is about maybe 2 times more expensive than reservation. So it is a common formula, a recipe for people to estimate their daily maximum consumption and reserve just a little bit on the top of that. But what you don't realize is that a lot of your consumption you actually only need it for 3 hours or 4 hours a day. So it's actually cheaper for you to buy them for 4 hours on demand than a reservation. However, the real situation can be even a little bit more tricky because the other risk of running on demand is you probably can't get that machine at a time. So it requires a little bit calculation, more sophisticated than just a single number. But I agree with you. Usually you should try to optimize your cost by reserve the right amount of machines. So the second question you have is about all those model optimization details. I think it would take a very, very deep conversation about all those optimizations. But one thing I do want to just highlight is the optimization for inferencing is actually quite different to the optimization during the training. So during inferencing, the scheduler of computation is unpredictable. Basically, you get requests coming from everywhere, and the requests are not pre-batched. How do you coordinate those requests? How do you find the maximum batching rate? This is more critical during the inferencing workflow rather than the training workflow. Hope this answers your question.
Any further questions?
There's one.
Hey, thank you for the excellent presentation. My name is Prashant. I work for Bull. So the AI hypercomputer, is this available in the distributed cloud? Or are you sort of connected with the distributed cloud for sovereignty?
Good question. So the Google Distributed Cloud solution is our on-prem air-gapped solution in which we bring in our best compute and best storage and our orchestration layer. We do not, at the moment, have the same the same stack that we run in the Google Cloud for the scale. And the reason being it's an apples to oranges comparison. But our GDC solution is optimized for running GPU workloads, and it brings in the learnings that we have in the AI hypercomputer in that form factor. When we talk about the AI hypercomputer here, it's a cloud scale form factor, and you get a slice of it. But we do bring in the learnings and best practices from the and the GDC format. I'm happy to go more deep in that. And we right now only have a GPU-based solution in that space.